Hello everyone. In this video we are going to look at another application of eigenvectors, or those mode shapes that I talked about in my previous video. Remember, I showed you that if you have a free response and you have starting from rest with some initial condition, you can find the weights of the frequencies, the natural frequencies of the system that exist in the free response using the matrix formed by these eigenvectors, the modal matrix, and the initial condition, right? And like if there is a node or anything. In this video, we're going to see another application called decoupling of modes, right? Decoupling of equations, really. And that is due to some property of these eigenvectors called orthogonality. So what is that? Let's take a look. So let's take a look at a system in free vibrations, mx double dot plus kx equals 0. And so here I keep k on the left side, not on the right. So k is positive on the left. And I take it to the right side, becomes mx double dot equals negative kx. And if you have a harmonic response in free vibrations that you do, then x double dot is going to be negative omega squared times x. So you can write it like this, and then you can basically go ahead, get rid of the two negatives, multiply both sides by m inverse, and you'll get this equation. And if you look at this equation, this is an eigenvalue problem, right? Because this is a matrix like A. So A times some vector equals some scalar times the vector. So this is an eigenvalue problem, right? Of the form this, right? Where V is the same as X and this lambda I is the same as omega n squared. So that's an eigenvalue problem. So as we talked about it, you can find the eigenvalues and eigenvectors lambda I and Vi from this matrix M inverse times K. Good? Fine. So now let me show you some other interesting things. So this equation, right? If you multiply both sides of it by M, right? So multiply both sides of it by M. M and M inverse would cancel, so you get KV on one side, you get lambda MV on the other side. Then you pre-multiply both sides of this by Vj transpose, not Vi transpose, by another eigenvector, Vj transpose, where here J is, of course, not equal to I. If you do that, then you'll get this equation down below. Okay? Or you can repeat this process, write the start equation about the jth eigenvalue and eigenvector, and then what? And then pre-multiply by Vi. So you can swap I and J, and then you get this equation 2. So you see 1 and 2 are exactly the same, just I and J are swapped, and you can get both of them. Now, one thing we remember about M and K matrix is that they are symmetric matrices. So you can say that Vj transpose KVI is the same as Vi transpose KVJ because it's symmetric. And similarly for M, Vj transpose MVI is the same as Vi transpose MVJ. Okay, so keep that in mind. M and K are symmetric matrices. We can write it like that. Now, what we do, we subtract 2 from 1. So it's going to be like 1 minus 2. If you do 1 minus 2, what will you get? Well, remember that Vj kVi is the same as Vi kVj. So the left side of 1 and 2 are the same. Look here. So when we subtract, they would cancel each other, right? The left-hand side would cancel. And so what will happen is you're just looking at the difference between the right-hand sides. And what is the right-hand side? Well, the Vj Vi and Vi transpose MVJ, they are the same thing, so you can factor it out. So it's going to be the common factor times lambda I minus lambda j, and then equal to the left hand side, which is 0. So you get this. Okay? Now, if I is not equal to j, or lambda I also not equal to lambda j, in other words, you have distinct eigenvalues. If your system has distinct eigenvalues, then since these two lambdas are not equal, this parenthesis cannot be equal to 0, so this guy has to be 0. So you get to this important result that Vj transpose MVI has to be 0, and if you plug it back into 1 or 2, right, when one side, the right hand side of 1 or 2 becomes 0, it means the left hand side is 0, so you get to this one. And these 4 and 5 are important equations. What do they say? They say Vj and Vi, these different eigenvectors, or the eigenvectors corresponding to different eigenvalues, are perpendicular to each other with respect to m or k. Remember, if for two vectors I have Vj transpose Vi equals 0, what do we say? When it's like the dot product of them, right? This is the same as saying Vj dot Vi, right? It's the same as this. When the dot product of two vectors is 0, we say those two are perpendicular or orthogonal to each other. Okay, right? So we say these two are what? Orthogonal to each other. But if there is a matrix in between and then the result is 0, so if you have something like this, now we don't say Vj and Vi are perpendicular to each other, we say they are perpendicular to each other with respect to m or k. So when we talked about orthogonality of eigenvectors, it's not like eigenvectors are perpendicular to each other with respect to m or k. So if you pre and post multiply by m or k, then that result is 0. And this is an important property. Why? I'll show you how we use this important property. So this is an important property. Now, what's the application? Let's take a look. So what should we do now with it? Here. So another thing before I start showing you the important application is we normalize the eigenvectors such that the magnitude of each one is equal to what? Equal to 1. If that's the case, I can show you that Vi transpose MVI, now they are the same index. If you pre and post multiply the vector by m, of course it's just going to be a scalar, right? This is always a scalar, and we call that MII, and if you do it without K matrix, then you call it KII. And this MII and KII, we call them generalized mass and generalized what? Stiffness. So I wanted to tell you about this extra definition, extra terminology, right? Generalized masses and generalized what? Stiffnesses, where I can go anywhere from 1 to n. N is the dimension of the status space, right? So keep these also in mind. So we learned some important properties, right? If the two indices are different, the result is 0. If they are the same, then it's a scalar. We call it generalized mass or generalized stiffness. Good. Now what we do is we use this matrix that I introduced to you in the previous video, formed by putting all these eigenvectors next to each other, and we call that what? The modal matrix. It's an important matrix that last time we used it to find the magnitudes of the terms in the free response. So now we have another application for it. So if instead of an individual eigenvector we pre and post multiply, if we pre and post multiply the entire matrix V by m and k, well, of course, now instead of one scalar, you get a diagonal matrix, where the diagonal elements are what? Are these m's and k's, these generalized masses and these generalized what? Stiffnesses, okay? So we can diagonalize m and k. Now, in the previous video, I showed you that the M matrix was diagonal. It's not always the case. So M is not always necessarily diagonal, okay? Most of the time it is, sometimes it might not be, and K is definitely not diagonal. They are both symmetric, but they are not always diagonal. But by pre and post multiplying the modal matrix transpose and the V itself to them, we can get them to be diagonal. And what's so good about diagonal? Let me show you. That's the decoupling. So what do we do here? If we start with the original governing equation, mx double dot plus kx equals 0, here we change variable from x to a new variable y such that x equals the V matrix times y. So here we do what? We do a variable change. We go from x to y, where again x is V times y. If we plug it in the equation, since V is constant, you get mvy double dot plus kvy equals 0. Now we pre-multiply both sides by V transpose and we get this. And guess what this one is? There we go. You're right. That is this diagonal matrix. And what is this guy? There we go. That's the other diagonal matrix. So now, in terms of the new variable y, look what happens to your governing equations in terms of y. Yes, you're right. The equations are now decoupled because, like, look at the first equation. What is going to be the first equation? It's going to be m11 y1 double dot plus k11 y1 equals what? 0. And it's the same for all other degrees of freedom. So you see now your degrees of freedom that you have, these y's, each one of them can be solved separately. You don't have both x and y in the same, both x1 and x2 in the same equation. Remember previously, and I show you in our next example, that this is the example we solved in the previous video, right? So m was diagonal, k wasn't. If you remember in the previous video, these were the two ODEs that I had. So in x1 equation, I also had x2. In x2 equation, I also had x1. So I had to solve them together. Remember, we called them coupled ODEs. You had to solve them together. But now look at these y's. This one, you can directly go ahead and solve it, right? So here, y1 of t is what? Well, of course, it's some constant a times what? Cosine of square root of k11 over m11, which is the natural frequency for that mode, times t, and then plus b times sine of the other thing, the same thing. Right? That's all it is. And you can do it for any other mode. They're all the same. So you see, the good thing is these equations are now what we call decoupled. There are n equations, but they are decoupled, and you can solve them individually instead of all of them together simultaneously. So that's the advantage. Now you get n decoupled ODEs. Okay? And once you found the y's, once you have all the yi's, how would you get back the original solution x? Well, go back to here. Pre-multiply all these y's by the V matrix and you get your solution x. Okay? So you transform your ODEs into a new space variable, in a new variable space in which the ODEs are decoupled. You solve the ODEs individually, and then using this transformation, go back and find the original solution instead of solving all of them at the same time. This is called decoupling, and it's an interesting property. Okay, so another way to talk about it is if we start with the original governing equations like this. So we just pre-multiply the original equation by m inverse, and we get this result. Now, similarly, instead of writing equations like that, it's like basically, or you can start from 8 and multiply both sides of it by inverse of this matrix, whatever this matrix you might call it. This is not the original m, But if this is like m prime or whatever, if you multiply both sides of this by inverse of this matrix, again, like maybe m prime, if you multiply both sides of this by this m prime inverse, this guy gonna go to I, so you just get this, and then this m prime inverse, when you multiply it by this new k, which you might call k prime, then you will get what? You will get the equations in this format, where these lambdas, each one of these lambdas are what? Is kii divided by mii. Okay, and these are the same as omega I, or omega is squared, and omega is omega ni, really, natural frequency. So another way to write this equation 8 is you can write it this way, and this matrix, this diagonal matrix with all the eigenvalues, you might call it big lambda. Okay, that's the same thing. But again, you clearly see that the equations are basically decoupled. So that's the same. Writing this equation, divide both sides of it by m11, and then calling this lambda 1. That's the same thing. So now let's look at an example. So here we start with the system that we had in the previous video. It was a 2DOF system, right? So you had mass m1, then you had a spring k1, then you have m2, and then you had k2, then it was attached to the ground. And we had some values for m1, k1, m2, k2. So if you remember, this guy was like 2, this guy was like 1, this guy was like a 100, and I assume this one was like 70. So this was the governing equation. These were the governing equations. And if you expand it, clearly you can see that the two governing ODEs are coupled. You have to solve them together. You cannot solve individually. But I say, let's use the modal matrix, which is basically the two eigenvectors put next to each other. So this is V1 and this is V2. Put them in a matrix and then use the transformation x equal Vy. And plug it back into the original equation. So you get mvy double dot plus kvy equals 0. You pre-multiply both sides of it by V transpose, and if you do so, then V transpose MV and V transpose KV are going to be these two diagonal matrices. Okay, so this guy is what? You're right, this is M11. This guy is what? M22. This guy is K11. This guy is K22. And in this case, remember, lambdas were different. Lambda 1 and lambda 2, they were not what? Equal. Okay, so we can use this orthogonality. And now, if you expand this equation, look what I get. Two decoupled ODEs. The first one is all about y1, the second one is all about y2. So I can simply what? Solve them individually, the same way I showed you, with two constants, a and b, c and d. And the first one only has the first frequency, omega 1. The second one has only what? Omega 2, or square root of lambda 1 and the square root of lambda 2, right? This one. Okay? Now, how do we find all of these four constants? Well, remember last time we started from 0 initial condition, initial velocities, and for initial condition we tried different scenarios. The one that had the mixture of both frequencies in it was 1 and 1 for both x10 and x20, the last scenario we checked in the MATLAB file. So we're going to look at this, right? And in this case, vector x dot at time 0, and remember this vector x is what? This is x1 and x2. So at time 0, both values are 0. And remember, x was what? X was v times y. So if you take derivative, x dot becomes what? V times y dot, and that's what I use down here. So x dot at 0 is v times y dot 0, and x dot at 0 is 0. We cannot be 0, so y dot at 0 is 0. That means both y1 and y2 are 0. And in these equations, if y1 and y2 are 0, what does that mean? Well, if the dots are 0, that means that when we take dots, this guy's going to be sine, this guy's going to be cosine. And the cosines at 0 are 1, so A and C will stay. The sines at 0 are 0, so B and D will disappear. So you get A equals 0 and C equals 0. In other words, there will be no sine term. You only will have cosine terms. And how do we find the cosine terms? Well, x, the vector x at time 0 equals v at time 0. So y at time 0 is v inverse at x0. And x at time 0 is what? 1 and 1. So this guy is what? 1 and 1. You multiply this v inverse. Remember what v was? V is this guy. We multiply inverse of that V matrix by 1 and 1, and this is going to be what? Y1 and Y2 at time 0, so those two numbers are B and what? D. So if you plug them in, your Y1 becomes this function, your Y2 becomes this function here. So I have my Y1 and Y2 solutions, and x is v times y, so we multiply that v matrix by y1 and y2, and we'll get x1 to be this and x2 to be this. And if you look at the solution of last time, we exactly got the same thing. Let me see if I can bring it for you. Guess it was here. Yes. Let's see. So here, you see, we tried 1 and 1, and these were the two solutions. And if you look at those numbers and the frequencies, that's the exact same thing that we found this time. Right? So we can go either way, but this decoupled way, you can always get it to solve easily because your ODEs, as I said, are what? Decoupled. So you can solve them individually. Okay? And one thing I have to mention is that this decoupling is not only useful when you have free vibrations like that. If you have force vibrations, it is also useful, and it might be even more useful. So if you have force vibrations like mx double dot and then plus kx equals f, and this f is like some harmonic function or any other function. Now again, because this k is not diagonal, you will have mixed, you have the coupled ODE. So this time you might get something like this. Let me just clean up a little bit, it's just too busy here. You'll get something like this, but maybe now instead of these zeros, you have, for example, 3 times sine of 5t, something like that. And this second one might even be 0, or it might not. It might be something else. Okay, it might be something different. Now how would you solve? So this one might be 6 times cosine of 40. Okay, so a system is harmonically excited. It's force response, force vibrations. Now how would you solve? Well, here is more complicated because not only they are coupled, these two have different frequencies and different amplitudes too. So now what you do is, again, use the same trick. Replace this x with v times y. And we pre-multiply both sides by v transpose also. So you get v transpose times m times v times y double dot equals what? equals, plus, I'm sorry, plus V transpose K times V times Y equals V transpose times F. And this is going to be diagonal, this is going to be diagonal, this is not. But this V transpose times F, it's going to create a mixture of what? It's going to create a mixture of both of these harmonic functions for what? For my system, right? So your equations will be something like this. You'll get M11 Y1 double dots plus K11 Y1 equals, now remember this V was something like, if you want to call it V11, V12, or 21, then V12 and V22, right? There's 4 components in this case. So if you transpose it, these two will be switched. And when you multiply it by F, then V11 will be multiplied by the first element in F, V21 is going to be multiplied by second element in F. And remember those guys we used were what? Were 3, 5, 6, 4. So we had 3, 5, and 6, 4, something like that. So this is your first ODE, and your second ODE is going to be this. Let me write it for you. So this is going to be 3 sine 5t. This is going to be 6 times cosine 5t, 4t. Okay, but the good thing is, if you look at both of these ODEs, again, they are decoupled, so each one can be solved separately for itself. So in this case, y1 is what? y1 of t? Well, it has a homogeneous solution, right, which is like a times cosine of square root of k11 over m11t plus b times sine of the same frequency. This is the homogeneous solution. And then plus the particular solution. So this is y1 homogeneous. And the particular depends on what? Depends on this function. If it's cosine 4t, it has to be cosine 4t plus some phase and plus some amplitude. And this is the amplitude of the input. So it's going to be some amplitude modification function, like some f times 6v to 1 times cosine of what? Cosine of 4t plus some phi, you might call it phi1 and f1. This is the response for this cosine term, and you have something for the sine term, which is going to be similarly like f2 times, it was 3v11, and then sine of 5t plus phi 2. And so this is what? This is your y1 particular. You see that? Okay. Let me resize it for you a little bit. There we go. You see? You find f1 and phi1, f2 and phi2 by plugging this y1p back into the governing equation and looking at the coefficients and find them. And then a and b are to be found from initial conditions, and similarly you can find y2 with a similar manner, right? y2 is also going to have a homogeneous solution. This time it's going to be K22 over M22, and these constants are going to be C and D, and then you will have what? F3, phi 3, F4, and phi 4, and these are the input amplitudes. So once you find y1 and y2 individually, then x is going to be what? V times y. So you see, instead of solving a 2 DOF system at the same time, you solve two separate 1 DOF systems, which you can easily do from your knowledge on vibrations of single DOF systems. And then what? Then you plug them here and you find the response of the second order system. Right? So it's the divide and conquer. Instead of attacking a 2 DOF system, you attack two 1 DOF systems. That's all this decoupling does. Hopefully it does make sense to you. And here is a simple MATLAB code for here. The M and K that we used, I used the inv of M times K for the A matrix, found the eigenvalues and eigenvectors, the natural frequencies, the eigenvectors, and then I show you V transpose MV, V transpose KV, and all of those individual elements. Remember, V1 transpose MV2, V2 transpose MV1, these two are supposed to be 0 because V1 and V2 are perpendicular or orthogonal with respect to M, to each other with respect to M. These guys should not. And similarly, these two in the K should be 0, and these two again are not. Okay, so here is just to show you the results, and if I run it in MATLAB, you see that these are the eigenvectors that we found last time. These are the natural frequencies. And look here, you see that V1 and V2 with respect to M are orthogonal. Also with respect to K, they are what? Orthogonal. But when you plug them into the same V and for M and K are used, you get M11, you get M22, you get K11, and you get K22. And if you divide this K22 by this M22 and take a square root, you'll get this frequency. If you divide this K11 by this M11 and take a square root, you'll get what? This frequency, okay? And this is the diagonalized M matrix, and this is the diagonalized what? K matrix. So hopefully altogether this made sense to you and you learned another application of what? Eigenvectors. Thank you so much for your attention. I'll see you in the next video.